let's look at an equation in one variable. So here it is. X equals 3 is our equation in one variable. And let's graph this equation in one variable. Okay, this would be a number line like we saw as young children in first or second grade or something like that. And 0 was in the middle, and then we'd go over 3. And that was, positive is in the right direction. And right, this is positive, this is negative. This is our X number line, and we would put a dot there at 3. And that's how we graphed X was 3. We just put a dot at 3, and that's what X is. Okay. Now we'll do an equation in two variables. And two variables we are very familiar with, because we've been doing them for years. We've been doing them all this course in Algebra 2 up until this point. This very point right now in this video, we're going to go on to three variables. That's what we've been doing, two variables. So how do we account for this second variable? How do we graph that? We're not at all unfamiliar with the idea of Descartes and the second number line, the number line that we call the y-axis. If I can make that blue. So we'll call this blue one the y-axis. And this is positive and this is negative. So if we want to graph all the solutions to this equation, well, x could still be 3, y would just have to be 0. And if this is the positive side of y and this is the negative side of y, and this is what we would put as the 0 for y. So yeah, x is 3 and y is 0, and so that totally works. What if we go over to x is 2, so we just march ourselves right over there. Well, if x is 2, then y, then going in the y direction, y would have to be 1. 2 plus 1 would be 3. Okay, that makes sense. Well, what if x were 1 instead? It was 1. Well, then y, we would have to move in the y direction. 2. There's 1. And let's say that's 2. Okay. What if x were 0? Then we would have to go in the y direction all the way up to 3 in order for this equation to be true. How about if we made x negative 1? Could we do that? Sure, we could go to negative 1 for x, and y would just have to make up for that and go up to 4. Okay. So we can graph all of these solutions, moving in the x and then the y direction, making sure that x and y add up to 3. And what I want you to think about in this video, in particular, and as we move into the third dimension, what shape is this making? What kind of shape are these equations making? Well, with these two variables, what we call a linear equation in two variables, we have just made a line. And think about our first equation, x equals 3. We just put a dot at 3. That's one dimension, a dot. Then we moved to two variables and we got a line. Well, that's a two-dimensional thing. So what are we going to do when we have x plus y plus a third variable, z? How are you going to draw this? How are we going to graph this equation in three variables? We went from one dimension to two dimensions to apparently it would make sense that we'd go to a third dimension. Well, we took the left-right dimension, that's taken. The up-down dimension, that's taken. And if we were to just throw like a diagonal line in there, that would just get confusing. So what we have to do is use the power of our human minds and be able to see a third dimension in a two-dimensional figure. So we have to imagine that we're going to throw another dimension in there that goes not left to right, not up and down, but toward and away from. Okay, so it's going to come out of the screen towards you and into the screen away from you. And it'll look something like this. Okay, that worked pretty nicely. It drew it thick here, and then as it gets further away, it gets thinner. Okay, so it's thick because it's close to you, and as we look at buildings or streets or whatever, they get smaller as they get farther away from us. So this is what we call the z-axis. This would be positive toward you and negative away from you. And so that's how we graph that third dimension. So now if x were 3, then definitely that would work. That dot would work. Y would be 0, z would be 0. That would work. But now that we have this third dimension, we could do something weird like we could do x is 3 and y is 1. And then to balance out that positive one and make sure that all three of these numbers added together make 3, we'll make z a negative. Make z a negative 1. So x is 3, y is positive 1, z is negative 1. And we add them all together and we get just 3. And you can imagine, I'll just do it a couple more. If x is 1 and y is negative 2, 1 minus 2 is negative 1. So z then, to make up that difference, so that they all add together to make 3, would have to be negative 4. So 1, 2, 3, 4. Not negative 4, sorry, positive 4. So it needs to come out 1, 2, 3, and that looks like it could be 4. Okay. So there's a possibility, one more possibility. X could be 1, y could be negative 1, and z then would have to be the whole thing. It would have to be 3, because 1 minus 1 would be 0, and z would have to be 3 in order for them all to add up to 3. So something like right there. Okay, so the thing that we want to think about is what kind of a shape is this going to make when we graph this 3-variable equation. Well, in one dimension, when we go back to one variable, in one dimension we got a dot. In 2 dimensions, in 2 variables, we got a line. A line could be like a 2-dimensional dot, like you were looking at a dot from just the end, but then you could look around the corner and see that it's a line. And now we need to move from a line to the third dimension, and we could imagine we were looking at the line really from the side, like looking at the piece of paper from the side, and if we peek over the edge, we get a piece of paper, or what we call a plane in math, or in lots of things. In science, we call these just flat things planes. So if we were to graph all of the points we possibly could in the 3 dimensions and connect them all together, what we would get, since all of these variables are to the first degree, to the first power, we would get this flat piece of paper type shape. Okay. Now the importance of the shape of this graph is, as we go into 3 equations and 3 unknowns, or systems of equations that have 3 variables, how can we, in what possible ways can we come up with solutions? Now that we know that they look like pieces of paper, how could we have solutions? Well, we could have one piece of paper like this. Okay, now in reality, these do go off forever in all directions. Okay, just like we have, we put arrows on the ends of lines when we graph them because they really go off in all directions. But we can imagine that they're just pieces of paper. What if there was another one that just intersected it like that? And then the third one could be down here, kind of like the corner of a room. Okay, remember that when we did section 3.1 and we graphed 2 lines, wherever they intersected was the solution. And the same is true for these planes. If these planes intersect, all 3 of them in the same place, then there's the solution. So there we go. That's the visual representation of a solution for 3 equations with 3 variables. So there's one way, that would be one solution, if they in some way intersect each other, all in the same place, all at one point. And that seems, if you randomly were able to throw pieces of paper in the air and they stayed that way, and you extend them off for infinity, more often than not, the odds are in your favor that they would intersect at some point, all three of them, like the corner of a room. Okay, maybe not exactly at that perfect 90-degree angle, but they would intersect each other at some point in space at one point. Okay, so what's another way that they could intersect? Let's imagine that here's a plane, and another plane is intersecting it just like that, kind of like a piece of paper folded in half, like that. And imagine this piece of paper is on its fold, sitting on like a table or a desk or something like that, and that's our third plane. Okay, so they intersect like this. They make this line that could go on forever and ever. And if we extended these two planes on forever, they would just keep touching this this third plane, or this desktop or tabletop or whatever, forever and ever. And so the solutions, the intersection for all three of these would be here, 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 here. Anywhere along this line would be a solution for all three of them. All three of them would touch forever and ever. So this would be infinite solutions. About another way, here's a plane like this, and imagine that I put another plane right on top of it, and another plane, a third plane, right on top of that one. Okay, and they're not even really on top of each other. They're even more than that. They are the same. They are inside each other. They are the same plane. And so the solutions are here, here, here. Anywhere that you find a point on the first plane, it's on all of the planes. And so this would be kind of the analogy for lines, would be if the two lines were on top of each other, they were the exact same line, it turned out. So this would be another way to have an infinite number of solutions. So what about no solutions? Is that possible? How about if, very similar to this, we had three planes on top of each other, except for they were slightly separated, right? So they're one above, actually above the others, and they are all perfectly flat, imagine. Those planes will never touch each other. They'll never intersect. So we have zero solutions here. And another way is, say we had a plane like this. Say we had another plane like this. Okay, so what they're doing is they're cutting each other like that. Okay, and there's this third plane back here like this. Okay, and this is like back in behind the rest of that stuff, so you can't really see it, but these two are intersecting over here, and these two are intersecting over here. And you can imagine the lines that these are making are shooting straight up. All of them are straight up, like pillars of a building or something. Now, these two are intersecting over here, making this line. These are intersecting, making this line, and these are intersecting, making this line. But all three of them, if they're all sitting straight up, all sitting in the same direction, then they'll never all three of them intersect like this guy does here. And definitely not like either of these. Until you angle one of them slightly so that it will eventually come and meet these other two somewhere over here, you have no solutions. So here's another zero solutions thing that can happen. Scenario. That's the word I was looking for. So in this intro video, that's all I want you to gain is, for one, something that was never explained to me, and that is what these graphs look like and kind of why, and how is it that we have solutions for three equations in three variables. Because when I was taught this, I thought, well, we'll have 3 dimensions, and now instead of lines in 2 dimensions like on a piece of paper, we'll have lines shooting off in all sorts of directions, And I thought, well, how could three lines intersect in 3 dimensions? Like, the odds aren't very good that it could happen. It could happen, but the odds aren't very good that it would happen. And yet, if you just make up 3 equations randomly, you will more often than not find that there is a solution for all of them. And that seems strange to me. So I wanted you to understand that the graphs of these equations are these pieces of paper, or these planes, and it's much easier to understand now that they could intersect at some point in space. And I want you to understand kind of what's happening, what's going on when we graph these, when we have one solution, infinite solutions, or 0 solutions. And don't fear too much. You don't have to graph these, at least not a whole lot. And certainly, we're not going to use graphing to solve them. We're going to use just like substitution and elimination, just like we had before with 2 equations. That's how we're going to solve these systems. So thanks for watching.